Good afternoon, guys. We're going to, in this video, create a staking smart contract. So we're going to make some payments to a contract and have it register that amount. And we're going to have a kind of reward incrementing based on the amount of time that the amount has been staked in the contract. And we're also going to have a claim method to redeem the reward that's accrued. During this lesson, I might go through a few things a bit quicker. For example, launching a contract, generating an account, and a few other things that we already went over in previous videos. So if you feel like I'm going too fast, it might be helpful to see the videos in chronological order because we do go over some of these things in detail. So if you're looking at something, you're like, I don't understand what this is. I most likely went over it in detail in previous videos, so just for everyone's sake, I'm going to go a bit faster on certain topics. For example, the first thing I'm going to do is import, just copy and paste the launch smart contract .py file. I'm just going to copy and paste. And we're going to create a .env, and we're going to define our algot token and algot server and a private key. And I'm going to quickly generate an account. Generate account.py from algosdk.account, import generate account, private key, address equal to. And then we're just going to print these. And we're going to take our private key. We're going to put in our .env. And then we're going to quickly go to bank.testnet.algorand.network and fund this address. We don't have to save the address, of course, because we can redeem that later. And then for the token, it's always blank. And the server for the public API, it's going to be on nodely.io if you need it again. Now that we have that, we're going to write the smart contract. I think we can get into that now. So I'm going to call it my staking contract.py. And from algopy, import arc4 contract. And from algopy.arc4, we're going to import the API method. And that should be enough to get started here. So we're going to create a class, staking contract, pass in the arc4 contract object. And for the initialization, we're just going to pass in self and return none because we won't need a global or local state for this contract. We might need box maps later, but for now, I'm going to show you regular boxes first, and we won't need to define anything there. So we're just going to pass the initialization. Then we're going to create an ABI method decorator here and define our first function. I'm going to call it stake. And we're going to pass in an argument here that we need to import GTXN, pay amount. There we go. Now we can see it. So G transaction allows you to access group transactions, transactions in the group transaction that we're submitting with this application call. So let's say the amount that they're sending to the contract to stake is going to be a payment transaction. You can also do asset transfer transactions, but for simplicity, we're going to do a payment transaction. And we're going to return a uint 64, and I'm going to import this up here so we can use it. And what we're going to return as a uint 64, the pay amounts dots amounts. And it's pretty simple so far. So we're passing in a payment transaction to our stake method as an argument. And then we're just going to return the amount that they sent. And we're going to compile this. I'll go git compile, py, and then the name of our file. So mine is called mystakingcontract.py. And assuming nothing goes wrong, let's see. Perfect. And if we go to our arc32, we'll see it only has one method here called stake. It accepts a payment transaction as an argument, and it returns a uint64. And we can see here the method, the name of the method, and the name of the parameter, which is going to be called payAmount. So let's create our application client. I'll call this file stake to contract.py. And before we start writing this, let's actually launch our contract. So we're going to go to launch smartcontract.py and make sure that, so global and local schemas, we don't need global or local states in our contract. So up here, for the approval teal file name and the clear teal file name, make sure it matches over here. So mine is capital S staking, capital C contract. So staking contract.approval.teal and staking contract.clear.teal. And as long as those match, and also make sure your node token, node server, and private key env keys match. So algod token, algod server, test user 1. And here I have algod token, algod server, private key. So I'm going to just adjust this here if you already had this template. And then that's pretty much it. We can run this. And remember, at the end of the launch smart contract, we fund the contract with 0.1 Algorand. This is 100,000 microalgos. And now we have our app ID down here. I'm going to go to my env and pass in the app ID. We pass it in like this, not in a string. But remember, we need to convert it to an integer anyways, because when we read from our env, it gets interpreted as a string. So let's get started here. Stake to contract.py. So from AlgoKit utils, import application client. And from algosdk.v2 client.algod, import algod client. And then import OS, so we can get objects from our information from our env. This is all something we did in previous videos. And let's set up our application client. I'll call it app client this time. And the first thing we need is an algod client, which we defined as algod client. Next, it needs the app spec. And for this, we need to import path from pathlib import path. And our path is going to be defined as path file parent / and then we're going to point to this file here, staking contract.arc32.json. That's our path. Next up, we need the app ID, which we just put in our end file as well. And we have to convert this to an integer. Pass that in here. And next up, we need the signer. And this we import from the atomic transaction composer, account transaction signer. So signer is equal to count transaction signer, and pass in our private key, which we have to import. Okay, next up, pass in the sender, and the sender is going to be the address that we get from our private key. And lastly, suggested parameters. So params, But client is where we fetch this method from, and it returns a suggested params object. And that's it for the application client. So we want to compose a method or compose a call, and we're going to pass in an atomic transaction composer, which we'll have to import here from the atomic transaction composer. ATC is equal to a new instance of a atomic transaction composer and call ABI method. And it is going to be called, as we see here, stake. That's the name of the method, the one that accepts the pay transaction. So we grab this word here, stake, pass it in as a string. And lastly, we need to pass in the payment transaction, which the parameter is named as pay amounts. And this is going to be equal to a payment transaction, which we're going to create now. And we get the payment transaction class from the transaction library. So we're going to say stake algo transaction is equal to payment transaction. Pass in the sender, which is us, our address. The SP is going to be the params, suggested params. Receiver, it's supposed to be the app address. And I'll show you something we need to change in the contract to make sure it's always the app address. And the amounts we're going to set to 0.1 algo. And if you're not sure, you can always import algos to microalgos from the algosdk.util. And that's it for the payment transaction. Okay. And you'll see that if I try to pass in and execute like this, it's going to tell me I need a transaction signer, transaction with signer, and we're passing in a payment transaction. So expected transaction with signer as method argument, but received, and then you have the raw payment transaction here. So what we need to do is import transaction with signer, and then we're going to say stake with signer transaction is equal to transaction with signer. And positionally, we're going to input the stake algo transaction and then our signer, which we have defined above. And now we can pass this instead of the stake algo transaction, now that it's wrapped with a signer. And we can execute this. And we should probably be ready to print the results. Print results.abi results. Let's get the transaction IDs first. So we know list. We know index notation. So we know that the transaction ID that we get back will be in the 0th position, the first index. And same with the ABI results. There's only one result. But I believe it's going to be in bytes. Actually, it might not be. Let's give it a shot and run this. See what happens here. It's definitely submitting. Okay. And we should have added this here, return value. So we're doing this twice now. Cool. So we got here the transaction ID. And we can go to AlgoKit, lower.algokit.io, and we'll see this payment transaction to our app. Or actually, yeah, to the app address. And what we're going to do here is in our contract, we're going to add an assert that the pay amounts transaction, the receiver is equal to. So we're comparing two values, not assigning a value to a variable. Going to import global so that we can get global.current application address. And what we're going to do now is we're going to write this information into a box. And we're going to go into boxes now. So BoxRef. And when you create a box, there's a key and a value, similar to a dictionary, but the key and value both have to be in bytes format. So if I have an integer and I want to put it into a box value, I have to convert it to bytes first. And then if I have, for example, an address that I want to use as the key, so I can identify the amounts with the address that sent it, I would need to convert that address to bytes and not have it in its base 32 encoded version like we see AlgoLearn addresses typically. So what we're going to do is, first we're going to create our box reference. So you can say staking box if you want, which is going to have the address as the key and the amount that they sent as the value is going to be equal to staking box equals BoxRef. And you'll see here it wants a key. That's all that it needs. So we're going to import something called TXN. And TXN references the current application call, the current transaction, typically. So if I wanted to get the sender, the person who's submitting this application call, this transaction, I would say TXN.sender. And as I said before, the key has to be in bytes. So if I try to compile this right now, it would tell me something like key expected bytes but received account. Argument key to BoxRef has incompatible type account expected byte string byte string. So this needs to be in bytes, and we can easily translate this to bytes by just accessing bytes, which is an attribute of transaction.sender. And now we won't get an error when we compile. And what we need to do, oh, I did not save. And what we need to do is we have to state, we need to find a way to kind of open this box and see the current value and also make sure that the box exists at all. And you can do this with returning two values, a tuple from staking box, which is now a box reference object, dot maybe. And what maybe does is retrieve the contents of the box if it exists, which will be the first value in the tuple, and return a Boolean indicating if the box exists, which is the second value. So if this box never existed, it would return none and false. And if it does exist, it'll return whatever bytes are in the box, followed by true, because it does exist. So we always need to confirm if the box exists, because there's a workflow you should adhere to when someone is staking. So if exists, so if this person, say, already has an amount staked with us, then amount staked is going to be value. And else, if it doesn't exist, we're going to create. So staking box dots creates the box. And this wants something called size. And we can't input this positionally. We have to use a parameter. And we're going to say 8, because for now we're only going to save in the box value the amounts that they've sent to the contract. So first we need to create it and define how many bytes we're going to need in the box, because this is a fixed definition for the box. So if I said the box is going to be size 1 or 1 byte, and then I try to put in 8 bytes, it's going to fail. It's not going to just put in 8 bytes and extend it automatically. So you have to define the box to the amounts of bytes that you're going to need. I could do 16 and then only put in 8 bytes and it'll only fill the first 8 if I splice, because it originally, when you create the box, it just fills it with zeros, 0 bytes. So you can always go back and adjust values later, or leave one part empty until another time. So we're going to create the box with size 8 for now, and then we're going to put into this box the pay amounts dot amounts. And you'll see here, this will fail. And I hope just for one reason, but we'll take a look here. Because payment amounts dot amounts is a uint64, and we need bytes. So we need this in bytes format, because as I said earlier, for boxes, keys and values must be in byte format. So similar to transaction.sender.bytes, you would expect that you could just hit .bytes, but it doesn't exist for payment amount. And what they have here is 2 uint64s. So there's the one we imported, and then there's another one from the arc4 library that's named exactly the same. So what I typically do is from algopy.arc4, import uint64 as arc4 uint64. So we get a custom name for the uint64 class from arc4, and then I can still use the original uint64 from algopy. So this one doesn't support converting to and from bytes. This one, the arc4 one, does. So what we need to do is create an arc4 instance from payment amount.amount and then convert it to bytes. And now if we compile this, you'll see that it is now able to put this value, this integer value, as bytes into the box. And we successfully compiled. So something we need to go back to, if exists, we can't just say amount staked equals value. This is incomplete. So what we're going to do here, so amount staked is equal to arc4 uint64 dots from bytes and get the current value of the box. So this is going to get the bytes format of the number and bring it back to us as an arc, as a uint64, so that we can then perform an arithmetic operation, addition, with the new pay amounts that they're submitting. So new amounts is going to be amount staked plus pay amounts dot amounts. And then similar here, we don't need to create the box because it already exists, but we do need to put the new amounts in there. And instead of payment amount dot amount here, we're going to put new amounts. And arithmetic in Puya is kind of finicky and very strict, so we need to make sure this works. It does not. So amount staked is wrapped as a uint_n. So what we can do simply is just get the native format from it. And now we have a uint64 and a uint64, now that we've removed the wrapping. And if all goes well, this should process fine. Perfect. So now what we're going to do is go back to our launch smart contract, launch this new version of the contract, get the app ID and replace it with the one here that we already have in our env. We're going to stake to the contract like we did before and see if we're going to get an error for invalid box reference. So a contract does not have knowledge of all of its information by default. I can't just tell a contract, hey, go get information from this box that you have. I have to actually sort of give it a ticket that says my box on it, and then they'll take that ticket and go fetch the box and come back to me. or allow us to read or write from the box through the contract and our method call to it. So what we need to do is kind of pass that ticket to the contract, and we can do that with transaction parameters. And it's going to be a dictionary, and in this dictionary we're going to create something called a key called boxes. And the value to boxes is going to be our BoxRef. And the BoxRef, or maybe we should say box key, that might be more accurate. So the box key, as we see in our contract that we just wrote, is going to be the sender of the transaction, the address as bytes. So we need to get the bytes format of the address in our code here to pass in to the contract because it knows it as bytes. So we need to tell it on the ticket the box name as bytes. And the way we can do that is, so there is from algosdk.encoding, you can import decode address, and it'll give you the address as bytes. You just pass in the address. But I want you to get into the habit of using ABI type. And the ABI type allows you to pass in any number of encoding schemes. So let's say I have in the box name 3 integers. So I passed in 3 arc4 uint64s and made that the box name. Instead of me manually decoding 3 numbers into bytes in my Python code here, and then putting them all together, concatenating them, just adding them together, I can actually just use this ABI type. And this is the recommended workflow that you use this ABI type, especially with arc4 contracts. So what we're going to do is we're going to define an ABI type, and we're going to call it address coder. So encoder and decoder. And this is going to be an ABI type from string. And we're going to define here in parentheses, as if it was a tuple, address. Decoded address is equal to address coder dots. And I believe it's going to be, we're decoding here. No. We're going to be encoding into bytes, which seems non-intuitive, the naming here, but, and then we're going to pass in our address here. And we're just going to print the decoded address so you can see what it looks like next to the actual address. And we're going to take this decoded address and pass it in as the box key. So what we should actually call this is the box key is going to be the address decoded. And when you pass in a box key, so boxes, the value needs to be a list of lists. So let me start from scratch here. So boxes is a list of lists. So it's going to be 2 pairs of square brackets. And in this list, within the list, you're going to pass in the app ID in the first index, the 0th index, and then you're going to pass in the box key afterwards, which if we hover over should be bytes. Perfect. And we're going to give this a try and see if it works. Cannot encode the following address. We need to pass in the address as a tuple and have it recognized by putting as a tuple by putting this comma in front. If you don't put the comma in, Python just says this isn't a tuple and automatically removes the parentheses. So we need to put in that comma after address in there. So we kind of tell Python, hey, I know there's only one object in this tuple, or one variable in this tuple, but I'm going to give you this comma so you know I still need it as a tuple. And that should work here. Perfect. So you see here, this is the address that we're using. And then this is the address as bytes. And then you can see we successfully submitted our transaction. This is the ID that we're printing here. And then the ABI result, we're still getting the 100,000 microalgo, which is the amount that we're sending here. 0.1 algo is 100,000 microalgo. So how do we know the box is actually there? Well, you could go to AlgoKit, I believe, LoRa.algokit, and grab the transaction ID here. So we have our application call paired with our payment transaction. We click the app ID here, which is at the top above its address, and we should see something called box here. And this is our box. So typically, you're not going to tell your code, hey, go to LoRa.algokit.io and click this tab and get the box name. So we need to manually pull up the box name for future use, or know how to in the for the future. So we're going to say get boxinfo.py. And here we're going to, might as well just copy and paste some of the stuff here. So we mostly just need the Algod client. So I'm just going to take this here and import Algod client and also OS. And Algod client has a method. Boxes is equal to Algod client dot application boxes. And then this just wants the app ID. And we're going to get that from our .env as well. So app ID is equal to os.getEnv. Pass in app ID, which is the key name here, our env. And this needs to be converted to an integer. And we're going to print boxes and see what we get. It's going to be a dictionary format. So we have here a dictionary with boxes. And the key boxes is equal to this value, which is a list. And this list contains dictionaries with a name key, and the value is a base 64 encoded version of our bytes. So to decode, well, first let's access this. So we learned about key notation in dictionaries and index notation in lists. So the first thing we need to access is the outermost entry point, which is boxes. So we're going to say, after we get this, we're going to say get the boxes key. And now we're going to go into the first index of this list, or the 0th index, the first item. So we're going to put 0 here. And then we want to get the name key, the value to the name key. So lastly, we'll put name here. And then we'll change our variable from boxes to something else, because now it's just a box. We'll say box name. And then what we want to do is decode this base 64 encoded box name. And we can do that with B64 decode from the base 64 library. And what we're going to do here is do, say on base 64 decoded box name is equal to B64 decode box name. And then when we print this, we're going to see we get this value here from earlier. Oop. Exactly the same. And this is actually our address decoded into bytes. So we're going to use the ABI, and we can just copy, we'll write it out. From algosdk.abi, import ABI type. And then our address coder is going to be ABI type.fromString, and it's just going to be a tuple with address. So a single value address to decode. And what we're going to do is we're going to say, it's weird to say decoded address because we're kind of encoding it. But let's just call it address then, is equal to address coder dots, I believe, decode. And then we're going to pass in the B64 decoded. Oh, B64 decoded. excuse me, box name. And then let's print the address and run this. It returns a list here. So we need to return the first value in that list. And then we'll get our AlgoLearn address. So now we just confirmed that the box name is our address as bytes. And what we want to do is we want to get the box value. So far we've only gotten the box name. So we're going to say the box value is equal to algo.client.applicationBox by name. And this allows you to pass in the box name as bytes. App ID, of course, included at first. And we have that value here, B64 decoded box name. That's how we got a bytes format earlier before we encoded it back into an address. So we're going to pass that in here. And we're going to print box value. And we're going to get a dictionary back. And it's going to have both the box name, the round it was created, I believe, and then it's going to have the value, and this is going to be base 64 encoded as well. So we can work similarly throughout this process here. So we can access the value directly like this. So now our box value is just the base 64 encoded string. And then we're going to say B64 decoded box value is equal to B64 decode and pass in the box value. When we print this, we'll see we're going to get 8 bytes. And we can print the length to confirm that it's 8 bytes because it's hard to tell with byte strings. 8 bytes. And this is going to be that 100,000 amounts. What we can do is we can create a uint64 decoder, or let's call it coder. An ABI type dot from string, and it's going to be a single tuple again, just uint64. And then we can say amount staked is equal to uint64 coder dot decode, and then we're going to pass in this B64 decoded box value. And when we print amount staked, we will get this number here, which we can access at the 0th index. Oh, what's going on? Put it within the parentheses. Now we have this number here. So, I mean, we're not really staking right now. We're kind of just depositing an amount to the contract and having it log that amount into its box value, into a box with the address as a box name and the amounts that they sent in the box value. It's not actually incrementing or generating rewards. So what we need to do is find a way for the contract to know how to accrue a reward for this person and later let them claim this reward. So in our contract, what we can do is we can increase the size of our box to 16. And for the second value, we're going to input, and we can get this from global.latest timestamp. And this is going to provide the current time in Unix time as a uint64. And we're going to need to use the arc4 uint64 and get the underlying bytes from this number. So now we're going to have the amounts that they just sent to the contract, their staked amount, and we're also going to have the time that they placed in the stake. So now we have a kind of way to measure based on time how much of a reward they should receive later. And we'll get into this, we'll make this more robust later, but we also need to adjust here. So if they're already staked, what we want to do is not overwrite the previous time that they staked, but we do want to increment the amounts. But at the same time, this can kind of be tricky because, so let's say I give you one algo, and you tell me in 10 days I'll give you 2 algo. I'll give you 100% return. And then on the 9th day, I come back to you and I say, hey, I want to give you 10 algo on top of the 1 algo I gave you, and I expect 22 algo tomorrow because tomorrow's the 10th day. And that might be the simplest way to explain that that's not how it works. You have to input it, wait 10 days, and then you receive your reward. You can't just throw a bunch of algo on the last day and then claim much more than you actually were intended to receive. So this is actually a kind of complex feature that I don't know if I'll go into in this episode. I might consider it as we near to the end, depending on how complex this gets. But for now, we're going to remove this if exists. And what we're going to do is just assert that it does not exist. So this only allows new stakers. So no one can come in and add an amount at this time. Maybe later in the video. So this looks good. And we're going to kind of simulate a reward accruing using this timestamp. And I'm just going to compile this for now, launch it, replace the app ID, stake an amount, and then we're going to look at the box info again. And you'll see here, if I try to run this get box info, again, it's going to fail. And that's because we're telling the ABI type object here, you're going to get one number. And it's clearly receiving, and it's going to be a UN64, which is 8 bytes. But this is clearly not 8 bytes anymore. If you print the length of the B64 decoded box value now, you'll see that it's 16 bytes. So what we need to do here is tell it to decode 2 integers. So you just add a comma, no spaces, and input UN64 a second time. And now when you run this, you'll get both values, assuming you don't print only the first index. So let me remove this here. Perfect. So now we get the first value, which is the 100,000 microalgo, or 0.1 algo. And then we get the second value here, which is a large number, which is a Unix timestamp. And you can get the current Unix time by importing time. And you can say, let's use an F string here, and say user currently has, and let's pass in amount staked, 0. And we can change this to box value info and say amount staked is equal to box value info 0 and initial stake time is equal to box value info, the second index. So user has this amount, and we can format this without decimals. Algo staked. User initially staked at, and we're going to pass in initial stake time, Unix time. And if we run this, just to make sure we have our, we don't need this 0 here. And if we print this, we'll see user currently has this much algo staked, and user initially staked at this number Unix time. And this number doesn't change. It's always going to be that number. But what we can do is we can say current time is equal to int time.time. And you don't really need to use integer, but sometimes it returns a float. So I just use this here so we don't have to see weird decimals. And we can say user has staked for, and we'll say here separately, time difference is equal to current time minus initial stake time. And we'll put in here another time difference. And we'll put in the 0 formatting again. Seconds. So this is how many seconds the user has been staked for. So 238 seconds since we initially staked. So what we can do is say for every second the user has staked, we can say reward is equal to time difference times, let's say 1,000 microalgo, which is the transaction fee for any transaction. So let's just say 1,000 microalgo. So how do we send them this reward when they want to claim? We can go back to our myStaking contract and create a new method and call it claim reward. Pass in self. And I don't think we need anything else. And we're going to return uint64 assert. Actually, we don't have to do that. So staking box is equal to BoxRef key transaction.sender.bytes. And only this person calling this contracts method is able to access their own box because the box name is the sender of the transaction. So that kind of, you don't have to really assert that the sender is equal to the box name because you get the box name directly through the sender. So let's say value exists is equal to stakingbox.maybe. Asserts that the box exists. You can't claim a reward if you haven't made a box yet. The amount staked is going to be equal to arg4 uint64 value, and the value is going to be 16 bytes. So we're going to use index notation to indicate with this colon from byte 0 to byte 8. That's going to be the amount staked. And we have to say here from bytes, create an integer. And we're going to do the same thing down here, where we're going to say initial stake time is equal to arg4 uint64 from bytes, and it's going to be from byte 8 to 16, from byte 8 to byte 16. And we're going to say time difference, similar to our Python code, is equal to global, this is how we get the current time, latest timestamp, minus initial stake time. And this should be okay, uint64, uint64. And the reward is going to be time difference times 1,000. And amount to send is going to be equal to reward plus amount staked. And then we're going to return amount to send. But first, we got to submit a transaction to the user from the contract. And we're going to import ITXN, which stands for inner transaction. And we're going to say ITXN.payment transaction, or payment. And we're going to say the receiver is equal to the sender for this application call. The amount is going to be equal to amount to send. And the fee is going to be global.min transaction fee. And that should be good. And at the end of this, we need to submit this inner transaction and return amount to send. So there should be a few errors, I hope. Well, not I hope, but I assume. Well, let's see here. Yeah, unsupported operand types, uint64 and uint, so wrapped uint64. That's going to be here. Initial stake time needs to be native, line 41. And then at line 44, similar situation. We're trying to add a uint64 with a wrapped uint64. So we're going to get the native version so we can perform addition on it. And now we should be good. Let's take a look here, see if it processes. Perfect. So we're going to launch our contract again. Place the app ID into our end file. And then we're going to stake to contract. And while we have an amount staked, we're going to remove these print statements. 100,000 algo, there you go. While we have some algo staked, we're going to duplicate this stake to contract and just rename it to claim reward or claim from contract. And in claim from contract, if you look at your arc32.json, we now have another method here called claim reward. And we're just going to replace this here, stake with claim reward. And our claim reward doesn't take any arguments. And it does return a uint64. So where do we go here? And we don't need to pass in this pay amount argument, but we still need to include the transaction parameter with the box reference within it. So this should be good. Let's check our box and see our current reward. So 70 seconds. So we should receive one issue. We need to fund our contract with some algo so that I can send, what's going on here? I gave it a transaction ID. Let me just get it from here. Okay. You can paste your app ID into LoRa, and it'll give you the creator and the account address, which we need here. Dispenser. There you go. And now we have staked for like 90 seconds now. So we're going to try claiming and see the reward that we've gotten, assuming this goes well. Perfect. So we received 230,000 microalgo as a reward. And this includes our 100,000 original stake amount. So we made 130,000 algo here. And there's something we need to go over before we go any further that I should have probably mentioned earlier. There's something called a box fee, and it's similar to minimum balance requirements for an account to opt into something. So if you opt into an asset, your Algorand address wants 0.1 algo forever until you opt out of that asset. And if you opt into an application, it reserves 0.1 algo in your account to be opted into that application as a minimum balance requirement. So if you opt into 10 assets, that's one algo in your wallet that you can never remove. It's going to be stuck there permanently until you opt out of those assets. And aside from opt-in fees for assets, applications, things like box fees, you also have that default 0.1 algo MBR for having an active account at all. So if you ever try to send everything out of your account, there will always be 0.1 algo that you can't remove without closing the account officially. You can always reactivate it by sending the 0.1 algo there again, but we're going to get into the MBR fee for boxes. So boxes are not free. Similar to opt-ins, they have a cost, and someone needs to recoup that cost. Usually this falls to the responsibility of the person sending the transaction to create the box. And we're going to do some math here to figure out how much algo we should be sending the contract when we stake. And to create a box, the box creation fee is 2,500 microalgo, which is 2.5 transactions. And then the box byte fee, so for every byte the box uses in either the name or the value, that's a 400 microalgo charge. So our current box is a 32 byte address. So address bytes is equal to 32. And then our UN64, two UN64s, is going to be 16 bytes. So the math here would be box MBR equals box creation fee plus address bytes plus UN64, two of them, two UN64s, times 400. And this should turn out to be, I think, 21,700. If we run this here, we'll get that amount. Yeah. And that is how much the contract needs, always, if it has those boxes written. So what we need to do to be scalable, because eventually this contract will just run out of algo, when they stake, we need to add a fee payment, which is just going to be another payment transaction. And we're going to assert that the fee payment dot amounts is equal to 21,700. And I use this underscore just to replace a comma, because you can't use commas in Python or Puya, Python, anything you use. So I do want to make this scale, but first let's just incorporate this. So in our stake to contract, we're just going to copy and paste our stake algo transaction and stake with signer. And we're going to change the amount to, I'm not going to use microalgos because I don't want to do math, 21,700. And we're going to rename this to fee payment transaction and fee payment with signer transaction. And now we just need to include this. So we're going to call it fee payment. And over here, we just say fee payment equals and pass in fee payment with signer. And of course, we need to change this here. And we're good. And in our contract, we already asserted that the receiver is the application. So I want to make this scalable. And it does take a bit of thinking. So if someone is already staking with us, how can we have them stake an additional amount? And I think the best way to do that would be, I think when they stake, if they already have a reward pending, then we can just dispense the reward here. We'll get this code here. We'll return this over here. And instead of asserting exists, if exists, we're going to do all this stuff that dispenses a reward. And then we're going to repeat what would typically happen, but without creation. So we're going to put the new amount that they sent and put a new timestamp. And if it doesn't exist, we're just going to put an else statement here and do what we would have done typically. And we'll set reward as another thing here that we return. We don't have to send them their full algo balance back. We can just send them the reward now. And instead of putting just the amounts that they sent now, we're going to say amount staked, new total stake is equal to amount staked plus the pay amounts dot amounts. So the new amount they just sent plus whatever they already had. It's going to be their new value here. And then we're going to put the current time and amount to send is now only going to be reward. Okay. And then over here, reward is going to be not defined. So we're just going to set reward equal to 0, or we'll say uint64 0, since this is expected to be a uint64. And then for claim reward, we should rename this to claim reward and withdraw. So this method they'll use when they want to remove their funds. Since they're withdrawing, we need to set their box BoxRef.put, and we're going to say arc4 uint64 0 bytes plus arc4 uint64 0 bytes. So we're going to send them, if they're withdrawing and claiming, we're going to send them all their stuff, their algo plus their reward, set the amount staked to 0, and the initial stake time to 0. So it kind of resets their box. We could even delete the box, and we'll do that. Instead of putting 0, we'll just delete it. Let's compile, see if we have any errors. Whoop. We have a trailing comma here we didn't remove. All right, unsupported operand types. This needs to be native on line 33. Mountstake.native. And then incompatible returned value type got tuple uint64 uint64. Expected uint64. Okay. I always forget it accepts the native tuple from Python, so we don't need to import tuple from anywhere. And we can just compile like so. Oh, we still have tuple here. And we're good. Okay, so let's test out the new stake and the new claim reward. And box maps will probably be part 2, if not part 3 at this point, because this is running a bit long. So let's go to launch. Use the new app ID. And then go over to stake. Let's check out problems. There's no comma here after our new fee parameter, an argument. And let's check current amounts reward. Okay, so we staked for 15 seconds. And let's try staking a second time and see what happens, because we input here that if they stake a second time and the box already exists, that they would receive their current reward, and then we would have their new stake amount and a new timestamp. So let's see if that works. So let's stake a second time. Okay. And we'll pull up this transaction here. Should be a group of 3. Oh, 4. Yeah, so we pay the 0.1 algo. The MBR fee, we actually only need to pay once. We could add something in there to make sure that only happens once. The app call and then the payment is the reward. So they were staked for 54 seconds. And let's claim. And we can see here the Unix time will probably have changed to the new stake time. Yep. And then if we claim from contract, found 0 methods for claim reward. We changed the name of the method to claim reward and withdraw. Let's run that again. Account balance for the contract is below. We just got to fund this guy one more time. The amount received back was 330,000, which is 0.33 algo. And we're going to cut this short. I'm going to show you the next part where we use box maps.